So here are two desiderata. How should we construct such a test? So let's begin. What do we anticipate from SN1, the number of elements in the sample in the first IQ bin? We anticipate that it should be close to n times P1. What about SN2, the number of elements in the sample in the second IQ bin? We anticipate it should be close to n times P2, and so on. And so it becomes natural to posit a test where we look at the difference or the distance from each Sn value to its expected value. Now, surely, following Kerner's second maxim, we want to take into account all the data. So why don't we simply look at how far Sn1 is from NP1, how far Sn2 is from NP2, and so on, and add them all up. Would this be a good test? What we anticipate is that if that sum is very large, then that would suggest that at least one of the Sn values is far from where we expect it to be. Now, superficially, this sounds reasonable, but then we realize very quickly that we are going to come a cropper, because the Sn values could be distributed on either sides of the expectation. And it is entirely possible to get a small sum where one element diverges far to the left of its expected value. In other words, we have a large negative digression, and another value accidentally cancels a large negative component by a large positive digression to the right. So we could have accidental cancellations of large positive and negative numbers, giving rise to a spurious feeling of normality, of that everything is okay, because the sum could be small, even though elements could be very large positive and very large negative. So this is not a good test. What could we do? Well, we realize that we are not interested really whether Sn is to the left or to the right of its expected value. We only want to know how far away it is. And so a natural idea might be, why don't we simply look at the square of these values? Now if we add them all up, if that sum is large, then we know that at least one of the Sn values is far from where we expect. This is beginning to sound promising. But on introspection, it falls foul of Kerner's second maxim, that we should make an effort to take into account all the data fairly. What does this mean? Recall that the first IQ bin has a very small probability, 0.02 or something like that. The IQ bin in the middle has got a relatively large probability, 10 times. Which means that in a random sample, there are going to be very many more elements in the middle than there are at the extremes. Which means that the estimates in the bins at the extremes are going to be underrepresented. They're not going to be fairly accounted for. To account for them fairly, then, we should renormalize by essentially the chances of falling into the bins, in other words, by the variability. And so it might come to our mind that the way to do this is to scale it so that everyone is on a common scale. And naturally, we'll scale by something like the variability, something proportional to the variance. Now we've got a sum of 8 contributions to deviations from where we expect these values to be. The contributions capture positive values because we're squaring. They're normalized, scaled by the variability of each of the bins, and now we have 8 components, each contributing in fair and just proportion. Pause for a moment to admire the elegance and beauty of such a simple expression, which we obtained by simple, basic principles, the maxims that I had touted earlier. Now, yes, from an algebraic point of view, it's a little messy, but surely, from a computational point of view, this is very easy. How do we do this? Generate a sample. Good. From what? From an underlying normal law. Good. From the sample, categorize the elements into which bins they fall. Determine the values Sn1, Sn2 through Sn8. Very simple. That's simply a matter of putting them into bins and counting. Compare each to the pre-calculated values n times p1, n times p2, n times p8. Remember, n is the sample size, is known to us, nominally 1,000, but it could be anything you like. p1 through p8 we've computed by looking at the areas under the curve. We know these values. Take a difference, that's a piece of cake, square it, simple observation. Divide by n times p1 through n times p8, that's easy, add them up. This is a computationally, trivially simple procedure. We can even conceive of doing it by hand if n is not too large, but assuredly on a modern-day digital computer, this can be done in a fraction and a trice. This is called a test statistic. Okay, the word is peculiar to statistics. It means something obtained by massaging the data, a simple numerical calculation using your sample. And this particular sum has been given a name, which has become enshrined by reasons of tradition and history. The name we give it is the Greek letter chi squared. So that sum is called chi squared, and it was articulated by Karl Pearson as a test in settings like this in 1900. So this chi squared, meaning that sum of 8 positive quantities, is called the chi squared test statistic. Now this is all well and good. At least this is a principled statistic. The idea is if this is a big number, whatever big means, then we are led to feel that there is an aberration. The data are not representative of what they should be. So this is the high-level intuition. But all this intuition and the philosophy will be worthless if we cannot characterize what the probability law of this statistic is. Remember, chi-squared is a chance-driven entity. It's a number, a positive number, obtained from a random data. What law characterizes it? A clue is given to us by the fact that each of the values Sn1 through Sn8 is binomially distributed, and they are, courtesy the De Moivre-Laplace theorem, individually, approximately, normally distributed. So this looks like we are summing the squares of normals and adding them. There's going to be a complication. The complication is that these values Sn1 through Sn8 are not independent. The reason being that the moment you put some elements into one bin, you have fewer elements to put in other bins. Right? So for example, if Sn1 is n, then everything went into the first bin, and we know that all the others are 0. There are dependencies across these. But nonetheless, these dependencies can be handled. The analysis is not at all easy. But we understand now that whatever the law for chi-squared is, it is going to emerge from an underlying normal law. This was calculated by Karl Pearson, and it turns out to have a beautiful, elegant representation. And I'm going to have no compunction about showing you the density for this law without telling you how to get it. After all, I haven't shown you a proof of the central limit theorem either. And so I would hope that certainly that you would at least be temporarily willing to take this on faith, that the law of chi-squared can be characterized. It is called a chi-squared distribution, and it is said to have 7 degrees of freedom. The terminology arises because, you see, the sum of Sn1 through Sn8 is exactly the sample size n. In other words, any 7 of them completely determine the last one. You only have 7 degrees of freedom. But I don't want to get into the technical details here. So this object, whatever it is, arises from an underlying normality, and it's called the chi-squared density with a certain number of degrees of freedom. As I've told you, the originator of this idea was Karl Pearson, and he was considered to perhaps be one of the fathers of statistics. In the very early part of the 20th century, he, together with R.A. Fisher in England, laid down much of the framework of what we use in modern statistics. I cannot resist the temptation to tell you a little anecdote about Karl Pearson. He was a formidable man, sometimes an irascible man. There's a biographical sketch provided by H.M. Walker in 1978 in the International Encyclopedia of Statistics, in which he attempts to sketch the character of this formidable intellectual. And here's what Walker says. Pearson was asked what was the first thing he could remember. He said it was sitting in a high chair, sucking his thumb. So presumably he was very young, a few years old. A person came to him and said that he should stop sucking his thumb, and that if he did not, it would wither and fall away. I took out my thumb, said he, put my two thumbs together, and looked at them for a long time. The thumb I suck does not look in any way smaller than the other. I wonder if she could be lying to me. And there, in this simple anecdote, in one fell swoop, you have, 1, a rejection of constituted authority in the form of presumably his nanny. 2, an appeal from a child to empirical evidence. 3, a belief in his own interpretation of the meaning of observed data. And 4, finally, an imputation of moral obliquity to a person whose assessment differed from his own. And there you have it, Karl Pearson at presumably age 3 or 4. Now, with this understanding of a statistical test, we now have a way forward to test Bird's IQ data. The question is, are the numbers reported for adults, children, aberrant? Well, how should we do this? Well, let us begin by constructing a 95% confidence interval. What does that mean? Select an interval where the chance of the chi-squared value falling in that interval is 0.95. Why 95%? Well, choose what you will. Replace it by 99%, you get a slightly different interval. Or 90%, you get a slightly bigger interval. It makes little matter. Pick a number, a confidence level that you're happy with. Let's say 95% for definiteness. Now, there are many ways of selecting an interval which captures 95% of the area under the chi-squared density. A natural way to try to do this is to sort of split the difference, as it were, to choose an interval where 2.5% of the area is to the left and 2.5% of the area is to the right. And if you did that, what we'll have done is essentially identify a left quantile, a value A, to the left of which the area under the curve is 0.025, together with a right quantile, B, chosen such that the area under the curve to the right of B is also 0.025. And a numerical calculation for this particular density with 7 degrees of freedom shows you that if you want a 95% confidence interval arranged symmetrically like this, then the left quantile is about 1.69, the right quantile is about 17.01. Now we've got a confidence interval. If you generate a random sample and then compute a statistic, a function of the data, a chi-squared, and if the chi-squared falls outside that interval, we will be inclined to treat it as aberrant. Here are 2 rejection criteria for potential putative data. The first, what happens if you get data, you compute a chi-squared value using this very simple formulation, and you find the chi-squared value exceeds the number 17.01. Well, you know the chance of this is very small, it's 2.5%. We reject the data with contumely on the grounds of an excessive irregularity. But there is another possibility. This possibility that I've outlined for you is what is typically done in a statistics package. But the form of the density also tells us that not only are large values for chi-squared not to be expected, but that very small values are also suspect. And so a second part of this test could be that if chi-squared, the value you compute from your data, is smaller than 1.69, we again reject the data, but this time on grounds of a too suspicious regularity. It's too good to be true. If every one of the Sn values lands exactly where we expect it, that is beginning to look a little like somebody cooked the books. It is making the case for fraud.